I'm Ryan. I'm a science teacher.
I'm Cheryl, and I slept through science.
Each episode will tackle a science question you may have learned in school, but can't quite remember or fully explain.
And I'll take the risk of asking the dumb questions so that we can all understand the science we slept through.
The bell has rung. Let's get started. Welcome to Lesson 11. Today, we're starting our hot and cold unit. We're going to be spending the next 7 lessons talking about things that are hot and things that are cold. Cheryl, what's your question this week?
So, Ryan, I was thinking about our second lesson where we talked about dissolving. And I have some follow-up questions for you. So
Perfect.
you like barely touched on that molecules change speed when they get hot and cold, but that's not what we were really talking about in that episode. And so
Right.
we just kind of said, like, that's a thing that happens. We'll talk about it later. And now it's later.
Now it's later.
So let's talk about it.
Okay. So we're talking about molecules moving when they're hot and cold?
Yeah, why?
That's a great question. So is the question, why are molecules moving, or why are they moving when they're hot and cold?
Yes.
Great.
Yep.
All right. Well, let's just start with a little pre-assessment. What do you think? Why do molecules, let's just start with this. What do you think a molecule is? And then the second question will be, why do you think they move?
I feel like you might have told me, and now I don't know if I remember, or maybe you
That's
didn't
okay.
tell me. It's small.
Okay.
It's different than a cell, probably, because they're different words. But they're both very small. They're microscopic. Molecules are ins. Molecules make up everything. And like an H2O, those are the molecules. That's what it is describing. I'm going to say that. We're going to stick with that answer. But as far as them moving, I actually, until you told me during that dissolving lesson that they move, didn't ever think about them moving unless the actual thing itself was moving. So like if I think about like something solid, I would assume like nothing in it is ever moving. But we're talking more about hot and cold. But like, so even a piece of ice, I guess, yeah, I think like piece of ice, I'd assume like, oh, well, nothing's moving. It's all frozen. So like it couldn't move. It's frozen. But then even if I think about like a glass of water that is sitting still and nothing is touching it, I would assume all of those molecules are just sitting there. They're nobody's moving until I like
a glass of liquid water.
Until I pour the water. Obviously it's moving because the water's moving. But like, so that was interesting when you were telling me that like it gets hot and they move faster and it gets cold and they move slower. I think if I had to guess, I would guess that those are the directions, but I don't really know like why that is. Like,
what do you mean directions?
Like if you told me one gets slower and one gets faster with a hot and cold, which is which, I think I could guess that.
Okay.
But I'm trying to think about why. Like, why would I guess that? Again, if something's frozen, I would just think like it's solid. It's frozen. It doesn't move. So does it have to do with solid, liquid, gas? Like if we think more about water, if it's like boiling, I would think it's moving more because there's bubbles. Like I can actually see the water moving. And then when it's a gas, it's like going up into the clouds real fast.
Okay.
So, but yeah, like are molecules in every object ever always moving to a certain extent? Or are there some things like my desk here where like nothing's moving? It's a desk.
It is a desk. I can confirm that. Even though we can't see it right now, I know that there is a desk there.
Yeah, this is kind of a question mark one for me.
Yeah. Awesome. All right. All right, Cheryl. So we're going to start with the basics and we'll build from there. Sound like a plan?
That sounds like a wonderful plan.
Great. We're going to start with what a molecule is, which is what I asked you. And you said they are small. You said they are different from cells, which is true because cells are also small. And you said they make up everything. And you used the example of H2O, right? Which is a water molecule. So you're right. H2O, water, that is a molecule. And a molecule is something that's made up of more than one atom. So the H,
right.
Yeah. So the H is hydrogen, which is an atom, and the O is oxygen, which is an atom. And so H2O means that there's two hydrogens and one oxygen. And we use the sciencey word is they're bonded or they're connected to each other. They're linked up so that they're kind of one thing. And that's what a molecule is. And you're right, they're small. They're way smaller than cells.
Okay.
Cells are made up of molecules.
Okay, yeah.
Some of them are relatively large molecules, like a fatty acid or a protein. Those can be really, really, really big molecules. Or there's a lot of water in our cells too, and those are pretty small molecules. So molecules do range in size, but they are generally smaller than cells. So
other than the part where you were fat shaming, I appreciate that explanation. No.
All I said was fatty acids, which are necessary for living things, by the way.
You mean having fat is okay? What?
Not only is it okay, it's healthy and it's good. Yeah. Okay. So with the molecules figured out, the next thing is you were basically asked the question because you weren't even sure, are molecules always moving? And the answer is yes, even in a solid.
Even in my desk?
Even in your desk.
So weird.
It is weird. And in order to help you understand why, I'm going to do a little sidestep, but I think it will hopefully make some sense for you. Temperature, what we call temperature, when you touch something and you say, oh, that thing is hot, for example, what's happening is those molecules have a certain amount of energy and they're banging into the cells in your hand, and your brain registers that and says, oh, there's a lot of energy coming into me right now because it's banging into me so much. That's hot.
Wow, this sounds really woo-woo, right? So interesting that this is like a more scientific explanation for why something feels hot.
Because what the scientific definition of temperature is the average kinetic energy of the molecules in whatever substance you're measuring. So let me break that down. You know what an average is?
Yep.
Right. You take all of the things and divide it by the number of things, right? The amount of whatever the thing is divided by the number of things you have. Kinetic energy, we've talked about briefly previously, but just as a reminder, that's just the energy of motion. So the more something is moving, the faster it's moving, the more kinetic energy it has.
Okay.
Okay.
Yep.
So what we call the temperature of something is the average of the kinetic energy of all of the molecules of that thing. So if those molecules are moving faster, which is what you said,
yep,
you said like if you had to figure out I think you called it the direction. If the average of all of those molecules is faster, it's hotter. We measure that as a higher temperature. What we are actually measuring is the motion of those molecules. That's what temperature actually is.
Wow.
And so the colder something is, like you said, the slower those molecules are moving, but they're still moving.
Wow. So if I put an ice cube under a really powerful microscope, I could see then I could see movement.
If that's the way microscopes worked, yes.
Is that not how they work?
Well, in order to see things that are that small, in order to see individual molecules, you have to use something called an electron microscope, which doesn't use light in the way that we think of a microscope. And so it really can't get the motion of things. It usually is getting a static image of things as opposed to things that are moving.
Oh, interesting.
Just because of the way that it works.
Well, you ever tried a telescope? Maybe that would work.
I haven't tried a telescope. I haven't looked at an ice cube in a telescope yet. I could. I think I have a telescope right down there on the floor, as a matter of fact, and ice cubes over in the fridge. So,
Oh my gosh. Interesting. Okay.
yeah. And so to pull it all the way down to kind of the most basic level of this, if you had an object where the molecules were not moving at all, there was no more motion, no kinetic energy of those molecules, we actually have a name for that. We call that absolute zero, which you may have heard of before.
Yes, I've heard that term, but I'm trying to remember where I've heard that term.
Probably on some science fiction show that they probably used it wrong. But absolute zero is actually the absolute coldest something can be.
Oh, yes.
The lowest temperature.
Yes.
Because you can't be moving any less than not moving at all.
That would make sense.
Right? Because you can't have negative motion.
Yeah.
Because negative motion is basically anytime we talk about negative motion in physics, it's usually motion in the opposite direction. But for this purpose, the direction doesn't matter. If something's moving backwards as opposed to forwards, it's still moving some, so it still has kinetic energy. So it's still going to be above that absolute zero mark.
So at absolute zero, does everything freeze?
The definition of freezing is turning into a solid.
Okay, so everything.
So your desk is frozen right now.
That's true. It is frozen.
Because it's a solid. So it is actually already, because it's not a liquid, it's not a gas. Yeah. So it's actually frozen. The microphone is frozen. Mm-hmm. That doesn't, we tend to, when we use the word freezing, we usually mean it in reference to water. That's like our reference point usually. And when things are really cold, they freeze because water is a really unique substance because it, under normal atmospheric conditions on Earth, we can see it in a solid state, a liquid state, and a gas state. Like we can do all three of those in our kitchen super easily and do all the time, right? So we tend to think of freezing as things being really cold because we think of liquids turning into solids. And if they're liquids at room temperature, then they must be freezing, getting colder to turn to a solid. But like, for example, butter is a solid at room temperature. So it's frozen. But it doesn't, you don't have to heat it up very much and then it'll melt. Mm-hmm. Yeah. But then it cools back down to room temperature and it freezes again, but it's not cold like ice.
Yeah. Yeah. It just has a different freezing point.
It does. Yes, it does. I've got a couple of visuals to sort of help with this for you, Cheryl, because I know that they're helpful for you.
Yes, they are. And if our listeners also want to be helped by visuals and you're listening to this as a podcast, you can hop on over to our YouTube page and watch us talk at each other and watch my face as I'm confused and as I'm learning. But probably more important, you can watch these visuals too.
So you talked about water as an example. So I decided to go ahead and use an example here with water. This is an interactive simulation from the PhET project through the University of Colorado in Boulder. So it's very, very cool. They got tons of really interactive things. You can click and try a whole bunch of things. This is each of those little kind of orange and two whites is an H2O, a water molecule. So the H are the two white ones. That's why there's two of them, H2. And then the orange one is the oxygen. And notice that they're wiggling. Do you see how they're wiggling?
Yeah, they're cute.
They are kind of cute. They're wiggling, but they're kind of like in this weird sort of structure with each other, but they are still moving.
Yeah.
And this is, of course, not perfect. That's a solid. So those molecules are sort of, in a sense, locked next to each other. They're not really moving around each other a ton, but they're still wiggling in place and moving in place.
Is that an ice cube?
So that would be an ice cube. Yes. Okay. Then we can go to a liquid. And you'll notice that for a liquid, they're moving a whole lot more. And you can see, especially along the top here, you can see how a number of those molecules are kind of like bouncing around and they're kind of turning and flopping around and things. And they can move past each other.
Yeah, it looks like popcorn.
It looks kind of like popcorn. And they're moving faster than they were when they were in a solid.
Yeah.
You see, I mean, I can go back. See, solid.
Yep.
More like wiggling in place, right? Wobbling kind of back and forth. Whereas liquid, they're kind of bouncing off of each other and moving around a little bit. So even in your glass of water sitting on your counter that's just sitting there, the molecules are moving around a little bit.
So weird.
If you wanted to be convinced that this is true, I have a really simple experiment you can do. Get a glass of water and let it sit on your counter for however long you want. And then if you have some food coloring, put 1 drop of food coloring, but don't drop it from super high up. Just drop it very, very near the surface so it doesn't splash or make the water move a ton, but just kind of add it to the water. And then that food coloring will spread out because the water molecules and the food coloring molecules are moving. And so they end up moving past each other and it spreads out.
Oh, okay.
That's also why, and then if you wanted to really do it with a room temperature and do it with hot water. Could even be like just below boiling. And the boiling one will spread out faster because the molecules are moving faster. So it bumps into things much more and the food coloring spreads out faster.
That makes sense. If I did it to an ice cube, I don't think it would ever reach the center of the ice cube.
Because
those molecules aren't ever changing places with each other.
Right.
So it's just going to freeze onto the ice cube.
Or if the ice cube starts to melt, or obviously you can get into more complicated things. Yeah.
Interesting. That makes, I could totally picture that. I just never thought about that being molecules, but yeah, it does itself in essentially over time.
Yeah, exactly right.
Cool.
Yeah. So I've got one more thing to show you with this, I think.
Well, but first, can I see gas?
Oh, okay, sure. Yep. So here's a gas.
Woo! Oh,
so you notice
party.
They are having a party. So you notice that they're no longer staying next to each other really in any way. They're bouncing off of each other. Some of them are spinning around in complete circles. They're bouncing off the sides of the container. They have a lot more energy and they're bouncing around and they're filling the whole container, which is what a gas does. Right? So think about when you inflate a balloon, it doesn't just fill the bottom of the balloon. Whereas if you fill a balloon with water, it just fills from the bottom because those molecules are all kind of stuck to each other. They don't have enough energy to move around each other. But when you fill it with air, those molecules have more energy. They're gas, so they can actually bounce off of all the sides of the balloon and fill the balloon up.
Interesting. So this is also how my humidifier works then.
Tell me what you mean.
My whole room.
Yes, it's going to take depending on how I don't know the specific humidifier, but yes, what it's probably doing is a couple of things. It's probably aerosolizing the water, which means making it, and you've heard of the term aerosol before.
Yes.
It's basically just taking something, usually a liquid, but technically I think you can do it with a solid as well, and making it into such tiny bits that it can float in the air.
Almost like a spray, but like finer than a spray.
Yeah, exactly. Okay.
So
how much of
not exactly how my humidifier works then?
It's related to how your humidifier works, but your humidifier generally is not just heating up water.
Yeah.
Right. It's usually doing something else to also, like, it as a spinner or as something that makes the water in really, really fine particles. So it also goes into the air.
Yeah.
But you could do it that way. If even just putting a pot of water on the stove and letting it boil.
My mom used to do that too on a dry day. Yeah.
Exactly. Right. Because it's doing the same thing. Yeah.
Cool.
Okay. Are you ready for the second treat?
Yes.
Okay. I'm really excited about this one because it's old school, but I also really like it and it might break your brain a little bit.
Yes. I'm so excited.
Are you ready?
Is it what your second tab says?
Uh-huh.
Bill Nye the Science Guy. Bill.
Yep. So this is a little clip from Bill Nye the Science Guy, the Heat episode, which is really, really good. I love the episode. It's great. I highly recommend watching it. But this is going to talk about temperature, but also heat, because heat is the actual energy, and temperature, remember, is the measure of the average kinetic energy. Okay.
Got it.
Are you ready for this? So this might make your brain hurt a little bit, or you might totally get it. I don't know. We'll see.
Here's a question. Which has more heat energy? This hot burning match or this beautiful ice sculpture of science? Well, the match is hot, right? The sculpture's cold. Well, they're both made of molecules, right? But which has more molecules? Well, the ice sculpture, a lot more molecules. So although they're much colder than the match, they actually have more heat energy. More molecules, more heat energy. Think of it this way. Suppose you tried to take a burning match and use it to melt the whole ice sculpture. Well, it's not going to happen, right? I mean, the match is going to run out of molecules long before the sculpture. So, more molecules, more heat energy. Ooh, ow, ow!
Careful.
He broke the swan.
So there you go.
Okay. The first thing I love about that is that for our listeners on the podcast, I was going to say he broke the swan to let them know what that crashing sound was, but then the video took care of that for me. So
he broke the swan.
I also was thinking actively, oh, how many matches did they have to go through so that it wouldn't burn out? And then he did a comical thing with like, ow, like it burnt out. So I haven't watched his show in years. Oh, that was
so good. Yeah. Does it make sense though, the example that he's talking about?
Yeah. So here's what it reminds me of. It reminds me of when we were talking about acceleration. You said that acceleration is just the change in speed.
Right.
And we commonly use the word deceleration, but really in science, slowing down is still acceleration.
Right.
And that's what it reminded me of with this. It's like heat energy isn't heat. It's heat energy.
Yes.
Not how we use the word heat.
Yeah. We tend to think of like temperature and heat interchangeably, whereas temperature is just that average. That's why the temperature of the frozen ice sculpture swan is lower than the temperature of the burning match, because the average, when you divide it by all the molecules, is lower. But the total amount of energy represented in that ice sculpture is so much higher. There's more energy, more heat in that ice sculpture because it has so many more molecules.
Yeah, interesting.
But the amount of energy per molecule, which is the temperature, that's the average, right, is lower.
Yeah. I'm not like 100% there, but it's like it pretty much makes sense to me.
Yeah. And it's okay. You don't need to fully understand it to understand what it is we're doing. But that's I think the answer to your question. Yes, molecules are always moving, and they're always moving because that's just what molecules do to not be at absolute zero. It's almost like a definition sort of a thing. Why are they always, what makes them move? Well, they have energy. They have some amount of energy to them. And so they are moving. And the amount that they're moving, we perceive in general as temperature.
Cool.
All right, Cheryl, it's time for your quiz.
Ryan, this is like why people don't like teachers.
People don't like teachers?
Did you not know that people don't like teachers?
Oh, no, trust me. This year, I know that people don't like teachers.
Oh, sad.
All right. First question. What are molecules?
Molecules are what make up everything. They're made of atoms. And a molecule makes up like a substance or like an anything. Like a water molecule makes water.
Good. That's good enough. Yeah.
Okay.
They are. They're made of atoms. They're different atoms that are bonded or connected together.
Groupings, maybe.
Sure. Yeah. What is temperature?
Okay. Temperature is the average of all the molecules' speed.
Yeah. Yep. The fancy science term is kinetic energy, but yeah, their speed, how fast they're moving.
Energy.
Mhm. Yep. What is absolute zero, Cheryl?
Absolute zero is when none of the molecules are moving. And I'm going to say it's when everything's frozen.
Sure.
How could it not be if it's
How
up
could it not be?
zero?
That's true. And I will just throw in as well, we have never had anything at absolute zero. We've been very close, but the problem is once you get things really, really cold, in order to measure its temperature, you add heat to it. There's no way to measure temperature without adding heat.
Oh, that's tricky. So this is like what scientists are trying to do.
There are scientists that's their entire career is trying to get to absolute zero or very close. I think we're in a couple hundredths of a degree, I think.
Wow.
But
What
not
is
actually there.
absolute zero in Fahrenheit?
I don't know. I can look it up. I know it in Celsius. It's negative
Okay.
273 in Celsius.
Okay.
Let me see. Absolute zero is negative 459.67 degrees Fahrenheit.
Wow. That's very cold.
It is very cold. That is correct. Colder than we have been.
Wow.
Yeah. Next question. What is the difference between a solid, a liquid, and a gas on a molecular level?
The amount of movement.
Can you tell me a little more?
Typically, a solid has the least amount of movement. Things aren't really moving places. They're just kind of wiggling around a little bit. And then in a liquid, they're moving a little bit, but not super fast, but they are moving more. And then in a gas, things are just like, man, like all bets are off. They're just going where the wind blows.
Literally. Last question. What are we feeling when we touch something that is hot?
Energy.
Can you be more specific?
Energy.
Of?
The molecules.
Doing what?
Moving.
Into
us.
There we go.
If it's really, really a lot of movement.
Yep.
Painful.
There you go.
I would also say if it was very, very cold, it would also be painful. But I feel like maybe there's some different reasons for that. Or is it?
It's actually a related reason. So trying to decide if this needs to be another episode. There's technically no such thing as cold as like a thing. Like things can be cold, but there is like you can have heat, but you can't have cold. You can have something that feels cold, but cold isn't a substance or a thing or a type of energy. And so when you feel something that's cold, what's actually happening is that's the way your brain interprets heat leaving your body.
Oh, okay. Cool. That was a good explanation.
Yeah.
Man,
little bonus at the end.
Science telling me that my essential oils don't really work the way I think they do and that cold isn't real. Bursting all the bubbles there, science.
I mean, the job of a scientist is to destroy everything that you thought was true. So.
I knew it.
Well, that's all we have for this week's lesson. So why don't you pack up your stuff and get ready for my closing remarks? You can follow us on Instagram and Facebook at I Slept Through Science or on Twitter at Slept Science.
If you have dumb science questions like I do, please send them to us. You can email us at isleptthroughscience@gmail.com, or you can even send us a voice memo and we'll play it on the podcast.
Please rate and review our podcast to tell other people what you think about it, subscribe to make sure you don't miss an episode, and share about our podcast on social media.
Thank you to Beth Reed Miller for the artwork. You can check out more of Beth's artwork at Beth Is Something. Okay, great. Tthanks. Bye.
The bell doesn't dismiss you. I dismiss you.